So first of all, I'd like to thank you all very much for attending this morning. I'm going to try and go through this quickly because I know your time is precious. We're going to go through some basic terminology and basic technology for in-building, and then ultimately talk about distributed fiber DAS for providing a good ERRCS solution. Not knowing the backgrounds of the audience, the technical stuff's going to be fairly high level, not real deep. If you do have any technical questions, I'd like to introduce someone who's with me here this morning is Stephen Chang, our product manager. So if anything I present technically is inaccurate, it's his fault. And as we go through the presentation, if you don't like anything you see in terms of diagrams, J.R. Wakabayashi is our marketing manager, that's his fault. So without further ado, my name is Don Henry. I'm the program manager for public safety here at COMBA. I want to give you a little bit of background on me, a little bit of background on COMBA, because many of you may have had the same reaction I did when the recruiter called me to join COMBA. I said, who or what the heck is a COMBA? So we're going to give you a little information on that. So I grew up in the IT industry selling some pretty complex IP networking products. Took some time away, got back into tech, and joined the DAS industry in 2008. I've sold many ERRCS solutions in many different verticals, many of them actually to LAPD and LA County out in California. I've been a member of APCO since 2008. Excuse me, got involved with Safer Buildings Coalition in 2017, and besides doing my job for COMBA, I'm very personally committed to providing high quality ERRCS solutions. Because, as I said, I took a few years out of the IT industry before I got into DAS. I spent a few years as a law enforcement officer, and in a very frightening situation, I personally experienced the no in-building coverage problem. So this is very near and dear to my heart. So a little bit of background on COMBA Telecom. So COMBA Telecom was founded in 1997. We're a publicly traded global company based out of Hong Kong. So marketing, corporate governance, corporate finance is in Hong Kong. Research and development and manufacturing is in Guangzhou, China, which, if many of you don't know, is kind of like Silicon Valley in China. We finished 2016 globally at about 760 million. We actually are the third largest OEM manufacturer of RF amplifier products worldwide. We specialize in providing high efficiency, linear power RF amplifiers, and we'll talk about that a little bit later. We, around the world, provide product to commercial operators, to base station manufacturers, et cetera. So we have a very large R&D team, very large manufacturing capabilities. COMBA Telecom North America, who I work for, we opened in 2005. I've been with COMBA since about middle of 2015. We're a wholly owned subsidiary of COMBA Telecom Limited in Hong Kong. Again, in the US here, we offered commercial cellular RF amplification equipment to OEMs, base station vendors, operators, etc. We began selling our commercial cellular DAS in 2014. We entered the public safety market in 2016, launched our first product actually at last year's APCO National Show in Florida, our Class A bidirectional amplifier. It's been very well accepted in the industry. We've done very well with it. And we are also COMBA is a commercial APCO member and also a member of Safer Buildings Coalition. So again, just some basic things we want to cover here. So, I think we're all aware that first responders many times are in buildings and have no signal or signal that can't be used. This diagram just kind of shows why that happens. So on the downlink side, you have a signal coming off of the base station, donor site. By the time it goes through the open air and has some free air loss, has to penetrate the outside wall of that building, get through the inside walls, get past all the inside clutter. By the time the signal gets to the handheld, it's not there or it's largely unusable. And of course, similar problem on the uplink side when the first responder in the building is trying to get a call out. By the time the signal leaves his 2-watt or 5-watt handheld and goes through all the walls, gets to the outside air, gets to the base station, it's again not usable or barely usable. This next slide is kind of interesting. This is a slide that I put together a few years ago, initially for the commercial side of things, but this shows various construction materials and the effect it has on dampening or blocking RF. So the interesting thing is, look at the line for low E glass. You can see that at 800 megahertz, it has just about the same blocking capabilities as a concrete block wall. So there's a good reason why a lot of times you're in a building and your radio doesn't work. Now we're going to go through just a little bit of basic technology and terminology. And again, those of you who are technically astute, bear with. Again, I had to presume that there were some folks here that this is, not their, the technology side is not their first calling, so I want to make it understandable for everyone. So downlink, again, that refers to the signal that is sent from the network to the mobile devices. Uplink refers to a signal that is sent to the network by the mobile devices. Bidirectional amplifier, which is typically used in most ERRCS systems, receives a downlink signal from the network and amplifies it for distribution within the building. It also amplifies the uplink signal coming from the handheld device to get it sent back out to the public safety network. You'll hear, and you've seen the term DAS, it's an acronym for Distributed Antenna System. And basically that distributes the downlink signal from the BDA throughout the interior of the building, and is also part of the mechanism that picks up the uplink signal from the handhelds and gets it back out to the network. Passive DAS, that's a system where you have the bidirectional amplifier, donor antenna on the roof, and antennas inside the building, but the only active electronics is the bidirectional amplifier. An active fiber DAS, which is what we're going to talk about later today, always has a BDA and a donor antenna and the interior antennas, but it has additional amplifiers that are located throughout the building that assist in that process of distributing the signal. Isolation is another term we're going to talk about a little bit later here. And isolation is the difference in signal strength between two antennas, and that isolation level is determined by physical distance or physical separation between those two antennas. Oscillation, that's something we never want to have happen, and that's the duplication of an RF signal being amplified and re-amplified again by a bidirectional amplifier. And again, we'll go into that a little bit later. Another term we're going to mention later is time delay distortion, or TDI, and that's a phenomenon that occurs when you have two identical signals being received by a device, but they're received at different times, and that causes some problems. RF noise is, any non-desirable signal that is combined with the desired signal on the RF path. RF noise can come from spurious RF sources, and I want to point out that all RF amplifiers, including ours, which we believe are very, very good, generate noise. It's just a byproduct of the technology. Squelch control, that's a circuit built into electronics that's used to eliminate or reduce the RF noise that is generated by RF power amplifiers, and we do that by shutting off the unused channels. It eliminates introduction of noise onto the network, and it's turned on or off by detecting whether there's voice traffic on a channel or not. Class A channel filtering, and again, I've got a chart later to describe this a little bit. That's where you're putting in filters to pass specifically and only the desired channel frequencies that you want. It's referred to as narrowband filtering. Class B channel filtering is different. That's broader band filtering that passes a range of frequencies, which means it passes the channels you want, but could also pass other things that you don't want. And that's again referred to generally as broadband filtering. So this next chart here is kind of a pictorial of a Class B amplifier. So this is standard 800 meg public safety. We've got uplink and downlink, and what we've done here is you've seen the line in blue, the curly line in blue. That's a very representative that this amplifier will pass everything. The two lines, curved lines in green, represent the broadband filter. So as you can see, we've put a broadband filter with a range of 806 to 824 megahertz, and we've put in a broadband filter of 851 to 869 megahertz. So anything within that filter range will pass through. The little spikes in red represent the channels that you want to pass, but as you can see from this diagram, you're not only passing those, but you're going to pass anything else that's within the range of that filter. Oh yeah, sure. Oh, perfect, thank you. So some of the attributes of Class B is it's easier to set up the software when you're commissioning the system, and it's easier for future maintenance. What I mean by that is, again, going back to the fact that we've got broad range filters. If a jurisdiction decides to add 1 or 2 channels to the network, nothing has to be done at the BDA. As long as those channels are within the general broad range, they'll automatically get passed through. However, unused frequencies, both uplink and downlink, are amplified and passed through, which can create and put noise on the network. And because it's broadband filtering, we're not able to achieve some channel filtering based features such as channelized gain control and channelized squelch, and we'll talk about that a little bit later. This next diagram shows filtering for a Class A amplifier. So again, you can see we've got the long blue squiggly line signifies that this amplifier will pass everything. Again, we're using the same basic 800 public safety. But what these represent is in red are the active channels, and green are the individual filters that you're putting around each channel. So as you can see, the filters roll off very sharply before and after each one of those individual channels. Again, this is referred to as narrowband filtering. Attributes of Class A are it takes a bit more time for setup than Class B because, as you can see, you're not putting in one broadband filter, you're putting in multiple filters, one for each channel. However, minimum noise will be created and put on the network because the only noise that will be generated will be any noise that's on a channel that's actively being used. And because it is channelized filters, we can do some features like channelized gain control and channelized squelch. These next 2 charts talk about uplink squelch. This first chart shows broadband. So again, what we've got here is a number of channels. As you can see, they're in use, and the squelch, if it got turned on, would be across everything, all the channels. The problem with that is if you need to put squelch on, you're squelching everything, not just the unused channels, but also the used channels. And the squelch circuit is turned on and turned off based on seeing traffic. It's not going to be as responsive as quick. So you could end up squelching traffic for a brief period of time that you don't want to. Channelized uplink squelch is a little bit different. So again, these spikes represent the active channels in use. This bottom diagram indicates here where we've got 2 channels in use. The other channels, there's no traffic, so the squelch turns on and suppresses just those unused channels. So what that means is, even though there's no traffic on those channels, if we were passing them through, it'd be putting their little bit of noise on the network. We stop that from happening by squelching those channels down. Next chart is to talk about, remember one of the terms I mentioned was isolation and oscillation. So here's what happens. You have in green, this represents the original uplink signal. So the first responder's in the building, he keys up, signal goes to the DAS antenna, goes through to the BDA, gets sent up to the donor antenna, and it's now out the roof and on its way to the donor site. But what can happen is some of this signal can leak down, get picked up by one of the DAS antennas inside the building, sent back up through the BDA, so it now gets added to the original signal, and now what happens is the gain and the strength of that signal goes up. Now this is all happening in microsecond kind of bursts, so this problem continues to happen. So every time that signal gets leaked to the DAS antenna and sent back through over and over and over, every time that happens the signal gets stronger and stronger and stronger, and several things can happen. you can cause the power amplifier in the BDA to start to distort. It's called clipping, where the waveform actually gets squared off, causes a lot of distortion, adds noise to the signal, and if the gain continues to go up and up and up, and by the way, that happening that's the oscillation part, it can actually desensitize the donor site receiver, because the donor site, of course, has gain control to protect itself from too strong signals. So we've got this signal problem caused by the oscillation, and it gets stronger and stronger and stronger, and the transceiver at the base station keeps turning the gain down. It might block this out. The problem is it blocks everybody else who's trying to connect in with a normal strength signal. So not a good thing. That's generally referred to as taking the network down. And obviously we don't want to do that. The next thing I wanted to talk about just quickly is, I mentioned time delay interference, or TDI. And again, as I mentioned, that's when you have a device receiving a duplicate. It's receiving the, quote unquote original signal. It's also receiving a duplicate, which is okay if they both arrive at the same time. If they don't arrive at the same time, then you have time delay interference. And what that means is, as the two signals arriving, as the delay gets longer and longer and longer, what ends up happening is it goes from kind of garbled to really garbled to words being dropped. And if the delay is long enough, one signal can actually cancel out the other, resulting in no signal. Again, not a good thing. So now I want to talk about some examples of ERRCS systems in a large building. So this next chart is a very, very typical depiction of the projects that our integrators do every day with our product. So here you have a public safety donor site transmitting over the air to the building. You have a donor antenna on the roof of the building, and that donor antenna is connected over a half-inch coax to a bidirectional amplifier. And then that bidirectional amplifier is in turn connected to the interior antennas, or service antennas as we call them, and the handheld devices inside the building talk to that service antenna. So as I mentioned, we launched our first product last year at APCO. It's a 2-watt per band, 700, 800 BDA. We tell our integrators you can safely presume that a 2-watt BDA can cover a building up to about 400,000 square feet. And remember, I mentioned passive system versus active fiber DAS. This is a passive system because, again, the only active electronics is the bidirectional amplifier. Now let's talk about what happens when you need to cover more than 400,000 square feet. So here we have a 1 million square foot, 12 to 14 story building. One solution could be you put in a 5-watt BDA. So it's a bidirectional amplifier. Again, this is a passive system, but it's got 5 watts of power instead of 2, which means you'll be able to cover that 1 million square feet. The potential problems are it's less than ideal power distribution, or distribution of the downlink power, because you're going to have that BDA sitting either in the basement or up in the penthouse. You've got some very, 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 very long coax runs and a lot of passive components to get that signal out to all those antennas that are going to be probably on every floor going up and down that building. And it's difficult balancing for system performance. So when the IB wave designer who does a design for the system, one of the things he has to do is call link budgeting. And that's making sure that all the loss from the coax and the passive connectors and everything is all balanced out, so you end up with a uniform signal no matter where you are in the building. It makes that more difficult. And there can be some additional cost concerns because that half-inch coax is quite expensive, and the cost for an integrator to pull that coax and terminate it is also very, very expensive, and that cost gets passed on to the building owner. And what we're all trying to do is keep the cost to the building owner as low as possible, so the more building owners say, yes, I want to put in a system to help the first responders. Another approach you can do is, instead of putting in a 5-watt BDA, you could put in 3 2-watt BDAs. So again, if we say a 2-watt BDA will cover 400,000 square feet, and you have 1 million, say, well, simple mathematics says I need 3 of them. So you could do 3 2-watt BDAs, and hopefully you've got a strong enough donor signal that you could have one donor antenna and split that out and share it to each of those 3 BDAs. The problem is you may not have a strong enough signal to be able to split it, because every time you split that signal, you cut the signal strength in half. So whatever the signal strength would be at the roof, coming down that coax, split it to go to the second BDA, the signal strength just dropped in half. Split it again to go to the third BDA, now it just dropped in half again. So it's possible that you wouldn't have sufficient signal to fire those 3 BDAs, in which case you'd have to have each BDA have its own donor antenna, and that can cause problems of isolation and oscillation, and can cause problems of TDI, time delay interference. And then there's some cost concerns as well, and that's, again, you've got additional half-inch coax and passives, so you've got the materials cost and the labor cost to install that additional coax and passives. Now we're going to show what it would look like if you did that with a fiber DAS, and you're getting a little sneak preview because this diagram is based on COMBA's fiber DAS that we're just announcing and launching at this show, and I've got some slides with some more detail on that later on. So again, we have the same hypothetical 1 million square foot, 12 to 14 floor building, but what we have is we have the donor site talking to the donor antenna going coax down to the master unit, but then we come out of the master unit over fiber, and we go with fiber out to 3 fiber remote units that are strategically located through the building, and then each of those supports some number of antennas. So one of the differences you can see is, if you remember back to the previous slide where we had one 5-watt BDA covering that whole building. So let's say, for conversation's sake, that 5-watt BDA was firing 60 antennas. In a design using fiber remotes, each remote would support 20 antennas. So each fiber remote with 2 watts of power supports a smaller number of antennas. So you're going to, again, have better distribution of power. It's going to be much easier for the designer to ensure, good quality signal throughout the building. The other thing is it eliminates the potential for donor-to-donor isolation issues. Eliminates or greatly reduces the potential for TDI, time delay interference issues. Again, versus multiple donor antennas. As I mentioned, better distribution of downlink power and cost reduction, because what used to be really long coax runs vertically is now fiber. Fiber is very inexpensive to buy and very expensive to install, and you've got a lot less coax going out horizontally from each remote to the service antennas throughout the building. Now let's talk about multi-building or campus examples. So again, here we've got the donor site. We've got 3 buildings, 3 400,000 square foot buildings, each with a 2-watt BDA. The potential problems you have with doing it this way is you can have donor-to-donor isolation problems. If you remember back to the slide that talked about isolation and oscillation, it's when signal leaks from one antenna to another and gets re-amplified. You can have that going on not only from a donor antenna and a DAS antenna inside a building, you can actually have that problem going on between buildings. So one of the problems with multiple BDAs on buildings that are in close proximity is that. And again, you can also have time delay interference problems because the signal's not arriving exactly at the right time. Cost concerns, again, multiple donor antennas. Donor antennas are expensive to put in. Not so much the antenna and putting it on the roof, but getting that coax up to the roof. More and more ordinances now are requiring that coax to be put in 2-hour fire-rated vertical chases. And it's, again, all cost that the building owner ends up having to bear. Now we're going to make it a little bit tougher. Now we've got, again, a 3-building situation, and the buildings are all 800,000 square feet, and so now we have to have multiple BDAs in each building. So again, you got the same problem we had before with multiple BDAs in a building of too much coax, too long a runs, et cetera. And you also have the potential problem of isolation between those donor antennas and all the time delay interference. So generally, multiple BDAs in buildings and multiple BDAs in campus buildings is not a good thing. So again, with a fiber DAS, you've got the donor site talks to the system through a donor antenna on the roof, but in this particular building, which is, we'd say, the main building on the campus, you have the master unit, and then over fiber you feed the remote in this building and you feed the remotes in the other two buildings. So again, this is all done over fiber. So you're eliminating the coax, you're eliminating the cost of coax and materials, et cetera. You greatly reduce the potential for time delay interference problems. You greatly reduce the potential, you've eliminated any chance of donor-to-donor isolation because you only have one donor antenna. So when is a fiber DAS solution a good idea? If it's a single building, and if a 2 watt or a 5 watt BDA will provide average coverage, even factoring in the link budgeting that I mentioned, the costs and things, then that's the best solution. Because the less amplifiers you have, always, the better off you are. It's the lowest cost and it's the easiest to commission and deploy. And for the following single building applications, however, a fiber DAS should be considered if the buildings are larger that can be reasonably adequately covered by a single BDA, or if the buildings have unusual floor plans, making it difficult to install a BDA, difficult to run the coax, etc. In those situations, a fiber DAS, even in a single building, is a good idea. For multiple building situations, a fiber DAS is the best solution when fiber is or can be available from the MDF in the main building out in a star configuration to the other buildings on the campus. Obviously, pretty much means all the buildings have to be under the same ownership or management. So if you have 4 or 5 independent buildings, even though they may all be required to put in a system, it's my building, I'm not going to help him with his building, So again, if they're all common ownership or common management, or if there are concerns about donor-to-donor or time delay interference issues. So these are all situations where fiber DAS is really the best solution. The difficulties with today's fiber DAS solutions are, we've talked about RF noise. Well, optical fiber also contributes some noise of its own. So optical laser noise floor can be a problem if too many remote units are deployed. Most fiber DAS systems today are Class B. Remember back we talked about Class B and Class A filtering and how Class A is just much tighter filtering and control over the channels. Most of the Class B remotes out there today, even those for public safety, are Class B. And so because they're Class B, it doesn't allow it to do any of the per channel things like per channel gain control, per channel squelch. And because they're Class B, they can introduce additional RF noise. And again, we try to keep all the noise off the network if we can. Most fiber remotes today that are available today are not NFPA compliant, meaning they don't provide the dry contact ports for alarming and reporting to the fire panel. And now we're seeing in some jurisdictions they want an on-site annunciator panel as well. And most of the fiber remotes out there today for public safety are not in a NEMA enclosure, so that means you have to buy a NEMA enclosure to install that remote in. And again, that's extra cost, takes up more space, etc. And then some fiber DAS solutions are converged, meaning cellular and public safety on the same DAS. Great potential for interference problems, but probably the single biggest thing that makes that a negative for the building owner is this last bullet. Greatly increase the cost for required battery backup. So those of you that are with HJs, probably you require in your ordinance that the public safety RCS system be battery backed up for 8 hours or 12 hours or 24 hours. If it's a converged DAS, that means the DAS head end and every remote, which has got amplifiers for all the operators plus public safety, that whole system has to be backed up, because there's no way on a fiber remote on a converged system you can say, well, we're only going to battery back up the public safety part, because they can't be separated out. So this really makes it very costly for the building owner. So when we decided to launch down the path of developing a fiber DAS, we made a decision that from a performance perspective and from a cost to the building owner perspective, doing a separate standalone fiber DAS was definitely the way to go. Now, they promised me if I came here and did a presentation at 9:30 and I finished within an hour, that my payback would be I could spend a little bit of time talking about our stuff. So I'm going to do that right now. So we call our product the Critical Point Fiber DAS Solution for Public Safety. I'll just go through some of the highlights. As I say, we're launching it at this show. We're in booth 1915. Invite you all to come by and see it live and in person, and talk in more detail with us. Any questions from what I've covered today, or any other questions you might have. But just basically, it's a dual band 700 and 800 meg system. It supports conventional public safety spectrum. We also support 700 meg band 14 LTE for FirstNet. It's a Class A design, so it's up to 32 channels per band, so it's 32 channels on 700, 32 channels on 800. We have channelized uplink gain control, and we have channelized uplink squelch, again to support both FDMA and TDMA environments. A question we get all the time, not all the time, but occasionally is, well, can you support digital and analog communications? Yes, we can, and yes, we can simultaneously. The thing to understand about DAS, and this is also true for cellular, is it's pretty much plumbing. It's like you put pipe in, you can spew liquid down that pipe. It doesn't care if it's hot water, cold water, Jack Daniel, Corona beer, whatever. It's liquid, it's a pipe, it goes down. So we don't inspect any traffic, we don't manipulate any traffic, we just pass traffic. So it could be analog, it could be digital, it can be both at the same time, no problem whatsoever. And we will provide a true end-to-end Class A solution. As I mentioned, most of the competitive DAS solutions out there, the remotes are Class B, broadband. So even if you put a Class A BDA in, that Class B is feeding a fiber DAS. If the remotes are Class B, it's really not a Class A system anymore. But both our head end unit and the remote will be fully Class A. One of the things we feature that we're really proud of is mandatory built-in isolation testing. Remember back to the slides where we talked about isolation? There's many problems where an integrator who may not know what he's doing puts in a system, he doesn't adequately test for isolation, puts the system on air, it immediately starts to oscillate and causes problems. So one of our competitors has isolation testing built into their unit, but if you don't want to do that, you just skip that step. We make it mandatory. So the first thing an integrator has to do is determine the isolation. Once he knows that, then he can set the gain in the system properly to make sure that it's going to compensate or work within the isolation parameters that he's determined. It's mandatory. They have to do that step before they can move on. 2 watts of composite downlink RF power, and again, that's per band. It's 2 watts downlink for 700, 2 watts downlink power for 800. It's going to be available AC or DC power configurations. The master unit will provide, and I've got a diagram that kind of shows it, will provide direct connection to the donor antenna, and the remote units provide the RF amplification, filtering connection to the indoor service antennas, and our system will support up to 8 fiber remotes per master unit. Now remember a little while ago I said, fiber adds some noise. There's some companies out there saying, oh, we can put 32 remotes, we can put 48 remotes. Okay, well, we probably could too. The problem is the fiber noise floor is going to be so horrendous, that's not going to work. So, we had a lot of input from our integrators, make this thing support 32, no, it's not the right way to do it. Our system is going to be easy to install and cost effective, so if you need that many remotes, do parallel systems. It's going to be much better, much quieter, much more manageable, etc. Fully NFPA compliant, will be UL and IC approved on our BDAs that we're selling today. We're FCC approved, we're UL approved, we're IC approved for Canada, and we're, I think, the only manufacturer who actually sports a decal that says we're also NEMA 4X. And again, another important thing is it's hard to aim at the and hit the right thing. So, yeah. So you notice here I say dry contacts for alarming are provided on both the master unit and the remote units. We're seeing some ordinances now that are starting to reflect fiber DAS, and they're now, instead of repeater, which was the buzzword that was in the ordinance for all these years, now it's been replaced with RF emitting devices, which is a BDA, but it's also a fiber remote. We're seeing some ordinances that say we want each RF emitting device to be able to report a failure separately on its own. We're seeing other ordinances where they're saying, no, we want all that alarming and reporting to come out of one central unit. So with our system, you'll be able to set it up either way. Either the master unit will report an alarm for all the remotes, or each remote can report an alarm separately. It's going to be flexible. Whatever the jurisdiction requires, the system will be able to set up to work that way. Configuration, commission, and management done via very easy to use, highly intuitive GUI. You'll be able to completely manage the system from the master unit when the integrator is putting the system in, because whether it's 2 remotes or 8 remotes, the channel count is the same, everything's the same, so he'll be able to go in and lay in the parameters for one remote and then automatically push that configuration out to the other remotes. And again, be able to be centrally managed. Both the head end and the remotes will come shipped in a NEMA enclosure. We support SNMP version 2 and 3, so our systems can even be monitored and managed remotely over an IP network or a cell modem. And we have very low power consumption. Remember one of my first slides, I said that COMBA's specialty is high efficiency linear power amplifiers. Some of the benefits of that are small footprint, very stable RF output, very low operating temperature, very low power requirement. So our units, our BDAs we're selling today in this fiber DAS will have much, much, much lower power drain than pretty much anything else out there. And again, because of the low power requirement, that's going to mean lower cost for UPS backup. Because if you have to back up a unit that draws 100 watts for 24 hours versus a unit that draws 300 watts for 24 hours, the 300 watts is going to require 3 times the batteries. And that's cost and that's space. And then also low weight and small footprint, again, largely because of the fact that we can do these high efficiency linear power amps. So I wanted to do a diagram to just show one of the other really key differences. So the top here is a typical competitive solution. So here you got donor antenna on the roof. They would have selected someone's BDA, hopefully ours, and then they're going to say, okay, now I got to connect that into the DAS head end, and then from the DAS head end, it's going to go out to the remotes. Well, with a typical competitive solution, a DAS head end consists of a DAS master unit, which is a 19-inch rack mount thing that you have to stick in a rack and then put in the proper modules for it. It's going to require another unit that goes in the rack that does the fiber optic conversion, that's going to take the signal out of here, RF over coax, and convert it into RF over fiber to send it out to the remotes. As I mentioned, these units have to go in a rack, so now they have to buy a rack and find some place to put it. And now that rack, to be NFPA compliant, ordinance compliant, has to be in a NEMA enclosure, so now they got to go buy a big NEMA enclosure to put over that rack. And then after there, you fiber out to the remotes, and the remote is going to have to be also put in a NEMA enclosure. So with our solution, we've essentially taken all of this and condensed it into one unit that's just about the size of a BDA that can be rack mounted, but can very easily be mounted on a wall. So that's got the connection to the donor antenna, it's got the channelizing and filtering, it's got the management console to manage all the remotes, it's got the fiber optics conversion, and it's got the NEMA enclosure, because it ships in the NEMA enclosure. Our chassis is NEMA enclosure. So what we've done is we've reduced a whole lot of space and a whole lot of cost. Then we come out to our remotes, and the remotes, again, ship in a NEMA enclosure. Their chassis is NEMA enclosure. And again, as I mentioned, all this stuff has to be battery backed up. So as you can imagine, the battery backup costs for the head end with our solution is going to be much less than it is up here, because you got to back up this and that. And our battery backup costs for the remote should be less than the competition, because again, we draw very, very, very low power. So again, no DAS head end, no rack size NEM enclosure. So just got kind of a quick estimate of the cost we save. And really these numbers represent the cost to the integrator. So you can basically mark those up 35 or 40%, and that becomes the cost to the end user. So, you know, we're saving $3,000 to $4,000 by not making them buy somebody's DAS head end. We're saving, you know, a few $100s for the rack. We're saving $2,000 to $4,000 for the NEM enclosure that would go over that rack. And obviously there's going to be much less installation costs, and as I mentioned, reduced battery backup costs. And it saves space. Again, no additional space for all the DAS head end stuff in the rack and the NEM enclosure. No rack required for the DAS head end, and all the actives can be wall mounted, both the head end unit as well as the remotes. We do have, for our BDAs now, they're wall mount. People sometimes say, I want to put it in a rack, or I need to, so we have rack mount adapter, and we will for these as well. But generally we say put it on the wall because, you know, it's up, out of the way, generally more wall space available than floor space to put a big rack. That's it. You didn't even have to raise your 5 minutes left, shut up, get off the stage sign, did you? Yes, sir.
What does the acronym ERRCS?
Oh, I'm sorry. So that's something that's fairly new. We've always called them, you know, in-building DAS for public safety. ERRCS is Emergency Responder Radio Communications Service. No, Emergency Responder Radio Coverage System. See, that's how new it is. I don't have it quite down yet. Yes, sir.
Between the master unit and the remote units, what's the distance that you cover? I think because we're talking about multiple buildings.
Miles.
Limitation on it.
Miles. Literally miles of fiber distance, yeah.
So let's say, for example, we had 15 miles between buildings.
15?
Let's say because
No, that's a little too many.
That's too far away.
What would you say?
That's too far away. I would say like 5 miles maximum.
Yeah, 5 miles probably, yeah.
from the map.
Yeah. Now, in a situation like that where you had really long run, there are solutions out there. We don't make them, but there's solutions from other vendors that can take that signal, amplify it, send it a long distance. Fiber retransmitters, maybe you might call them. Yes, sir.
So the boxes themselves, do they support any sort of redundancy? So let's say, for example, you've got a campus, you've got 5 buildings, you've got a master unit, right?
Mm-hmm.
Can you have 2 master units, one light hot, one standby? So let's say, for example, you do have an existing problem in one building, that building becomes compromised for some reason, you lose that master unit, but now you've got police going to another fight or some other problem in another building. Those remote units then don't amplify that signal because that master unit is now offline in that primary building. Is there anything you guys have talked about in terms of failover for situations like that?
On this first release, like we're looking at.
Yeah, I was.
Because this is the run from many other so
We're also looking into the ability to have redundancy at the remote end as well.
Yeah, because I was kind of thinking like I've got 25 like school buildings in my city. I've got single mode fiber at every single building. We own the fiber, we don't share it with anyone to start fiber. You know, what if I just co-located like 2 head ends somewhere, it's like a main standby failover that I have to be in my primary site and backup site. So I have good coverage and then feed each of those school buildings with over the single mode fiber and actually be able to sprinkle the remote units around. Even if I got to put battery backup on it, might, be better, but I can't do that if, there's no failover, there's none of those sort of things. If I lose one, I can't lose all 20 buildings.
Yeah. Good point. So again, not in the first iteration, but that and some other pretty trick things that I won't talk about now that we've got. So, you know, we're just bringing this to market now. We're already thinking next generation, so.
Any plans for UHF?
Yeah, as a matter of fact, we have on our roadmap for this year a UHF BDA. We also have on our roadmap for next year a 5-watt version of our 700, 800 BDA, and also VHF. And we're also have on our roadmap our own branded battery backup unit. It's not a lot of high-tech in battery backup, but we know we can produce a unit that's going to be very cost-effective. And nobody gets excited about battery. You know, people get excited about the DAS equipment because it's kind of cool and it does neat things. But battery backup is batteries, you know. So the key there is small footprint and low cost. So yeah, we are very committed. COMBA is very committed to public safety. And again, I'm part of what's driving that because of that little incident that I went through, where I told the department you need to change your written procedures now so that, you know, after an event like this, the officer is allowed to go home and change his underwear. Yes, sir.
Between the master unit and the bogies, is that single mode or multiple fiber?
Single mode and single strand.
And then what are some solutions between non-shared ownership of buildings that you have to have BDAs in, but they're different owners, they're not going to share a master unit? What, with the concern of oscillation and interference, what
Yeah.
are some of the typical solutions to avoid that?
No, it's tough, and I know, you know, we as a community will run into that. We, you know, and again, before I got COMBA into public safety, you know, when I was working for the integrators, I sold a lot of public safeties. I also sold cellular DAS systems, and I mean, here's a problem. Here's a 12-story building. It's owned by some management company, and they rent 4 floors out to a stockbroker. And he's like, I can't have my brokers going out in the parking lot to call a guy with a $30 million portfolio. It doesn't look good. I need to put this DAS thing in. The building owner says, well, I'm going to pay for it. Okay, well, what if I'm willing to pay for it? Would you share the cost? No. Well, okay, I'll pay for all of it. No, because now you're making a material change. So sometimes it ends up have to be some negotiating. Yeah, but if it's separate buildings, you know, separate owned buildings, then you have to say, I guess I have to do BDA in each building. And the thing is, you know, then that's where it's incumbent upon the integrator to be very good at what they do, you know, and be very experienced in this community that can design a system to mitigate the possibility as best they can. The other thing too is there could be, well, we haven't seen it too much yet, but there could be a campus with, you know, owned by, you know, it could be a hospital with a bunch of towers, or, you know, like out in Silicon Valley where COMBA is, you know, between Google, Apple, and Facebook, they all own, you know, 5 or 6 building little campuses all over the place. You know, we've seen campus environments where they never put any fiber in. Well, if there's no fiber and you wanted to do it, then you either got to put in fiber, which can be very expensive if you got to, you know, start, you know, cutting it and putting it into the ground and things, laying it into the ground. So it's just sometimes you just can't do it, even when it's all owned by one building owner. Yes, sir.
With fiber being fiber, what's the reason for limitation on distance between campus and building?
Well, so it's a matter of how much strength has. So once the signal's converted into a laser light signal, it has some loss as it goes along the fiber, and there's some noise. Always nice when the sales guy can answer a question. The engineer says, yeah, you did good. Yes, sir.
Is it just the signal strength or the latency as well between distance?
Yeah, there's some latency, and one of the things that always needs to be taken into consideration on any ERCS system, even if it's passive, but especially so when it's fiber, is latency, which can in fact, I don't know if I said it, but let me jump back here. Well, I thought I had it in here, but yeah, I meant to have in here a point that says a fiber DAS can contribute to delay. So again, that's why when a system is designed, a good integrator would come to us and say, okay, how much delay for each piece of hardware? I have to add that up, then calculate the delay going over the fiber and everything and come up with a composite delay number. Any other questions?
Just one.
Yes, sir.
Other than the answer, but as far as cost is concerned, retrofitting an older building that's, probably going to be decommissioned versus new construction, and integrating this sort of equipment into the construction of the building, so it's already wired while the building is being built, the cost would be cheaper on the new construction.
Absolutely, yeah. And depending on what the interior of that building is like, it could be a lot less expensive, because if it's drop lid, okay, well, you have to push up tiles and pull the cable and drop them back down. If it's hard lid, now you have to cut to retrofit. Now you have to cut access holes, get in there and pull the cable, and then when you're done, somebody has to come in and patch those access holes and sand it and paint it. And so yeah, so we're finding more and more building owners are saying, and especially out in California and other warm climates where everything's low E glass. You saw that chart. It's funny, I explain to people, I say, in the old days before low E glass, you saw two buildings, identical buildings, except one had a whole bunch of windows and one had very few. You'd look at the one with very few and you'd say, that's the building that's going to have the RF problem, because it's all brick wall, just a few windows. Now with low E glass, you see two identical buildings, one's got a lot of windows and one's got a few. The problem is more likely going to be on the building with a lot of windows, because the low E glass blocks worse than sheetrock and lumber walls. Yes, sir. Yeah, so it's channelized uplink and downlink. And at the remotes, yeah. See, and that's why, one of the reasons we said let's do it Class A end-to-end is one of the things, remember one of the slides was a channelized squelch. So again, the whole object is to get good strong signal out of the network and try to not put any noise on the network. So with the remotes being Class A, we can do squelch at the remote on the channels that have no traffic. If we didn't have that ability at the remote, if the remotes were Class B, then all those channels are open all the time. So whatever residual noise is going to come off the amplifier in that remote is going to get put onto the DAS, which is going to ultimately end up on the network. So yeah, so being able to do Class A at the remote end gives us some real advantages. Oh. It has an effect on delay. Yeah, the narrower the bandwidth, the greater the delay is. Yeah, so it's why on our Class A BDA that we're selling now, and will be on this, we're going to give you the ability to have 12.5, 25K, or 75K channel bandwidth. The wider the bandwidth, the lower the delay. Come on, somebody give me a question. Nobody's made me really squirm yet. I've had to point to Stephen a couple times, but any other questions? Okay, so again, thank you all very, very much. I know 9:30 on a Sunday morning, you probably could have found something more fun to do. I hope you found this enjoyable and informational. Again, we're in booth 1915 if you want to come by and chat with any of us or see the equipment in person, we'd love to have you come over. So again, thank you very much and have a good day.